Hi, my name is Aidan Simpson, and my project focuses on the evolution of stars within AGNs. An active galactic nucleus is the region at the center of a galaxy where material is producing radiation due to accretion onto a supermassive black hole. A black hole becomes active when matter falls onto it in the form of a disk around it. AGNs can be so bright that they outshine the entire galaxy that they're in. There are many types of AGNs, such as blazars, quasars, seed for galaxies, etc., and what differentiates these from one another is the viewing angle of the observer. There are two ways that stars can end up in this region of a galaxy. There's in situ formation, which is where stars form inside the disk of the AGN, and there's also capture, where stars that are formed outside the accretion disk interact with the disk, and as they interact with the disk, they slowly lose momentum, and eventually they are captured by the disk. In my project, both of these situations are treated the same way. Stellar evolution describes how a star changes over its lifetime. The lifetime of a star is primarily dependent on its mass, where smaller stars tend to have longer lifetimes, while more massive stars tend to have shorter lifetimes. The reason that smaller stars tend to live longer than larger stars is because larger stars burn brighter and hotter, so they burn through their fuel faster than the smaller stars that aren't as bright or hot. Stars evolve by fusing lighter elements into heavy elements. For example, a star can fuse hydrogen into helium, helium into carbon or oxygen, into etc. The last element that stars can fuse into is iron. Because stars would need to put in more energy to fuse iron than they would get out of the fusion. So this is where fusion stops and the star is left with an iron core. There are two main forces that are balanced by a star: gravity and the gradient of pressure. The gravitational force is dependent on the mass of the star, and there are different types of pressures that stars experience, mainly gas pressure, degeneracy pressure, and radiation pressure. The main types of pressure that a stars like our sun experience are gas pressure, as radiation and degeneracy pressure are very small in stars the mass and size of our sun. As stars become more massive, they become more luminous, increasing radiation pressure to the point where it is the dominating force. When radiation pressure becomes great enough to equal the force of gravity, matter on the surface of the star can begin levitating. This is what is called the Eddington limit. Whether stars are formed outside the AGN or inside the AGN, once the star is in the disk, it will start accreting matter from the disk onto itself due to the gravitational force of the star. This can be a runaway effect because the more matter a star pulls in, the more massive it becomes, meaning it has more gravitational force, meaning it pulls in more matter, etc. We know from stellar evolution that the more massive a star is, the more luminous it also becomes. After a certain point, the star becomes so luminous that it reaches the Eddington luminosity. And when it reaches the Eddington luminosity, the star begins to lose mass because the material on the surface is able to levitate. Stars can also affect the AGN because when they lose mass, they dump heavier materials onto the disk of the AGN, which can change the composition of the disk itself. The goal of my project is to simulate star evolutions in this region of space. What the simulation does is it essentially creates a box that replicates the conditions in this region and allows a star to evolve within this space given its initial parameters. My job is to decide where in the simulation it is necessary to implement a more complicated network of isotopes. What makes the network more complicated is the sheer amount of isotopes that it contains. The simpler network contains 21 isotopes that are sufficient for earlier burning stages of the star, and the more complicated network contains around 128 isotopes of elements. The reason why the simpler network is used at the beginning is because it allows the simulation to run faster than the complicated network. The complicated network is needed for when the star begins to burn heavier elements and there are more elements and isotopes in the star as a whole. The point where I decided to change the 21 isotope model to the 128 isotope model was when helium consisted of 10% of the star. This is around where oxygen burning begins to occur. To switch to the 128 model, I saved the end state of the 21 isotope simulation and then began that again with the new network. I ran this simulation until it wasn't able to run anymore and then recorded the final temperature of the star in the simulation. I then ran the 21 isotope simulation until it reached the same final temperature. I did this to compare the difference of the two simulations within the networks. The graph on the top left shows the mass of the star in the AGN disk over time. This is for the first simulation where the star begins to reach the point where helium consists of 10% of the star. As you can see, the star begins to lose mass after becoming very massive due to reaching the Eddington limit. The second graph on the left shows the evolution of stellar core composition of the star over time. The blue line represents how much of the star's core consists of hydrogen, and the yellow line is how much of the star's core consists of helium. This star burns through its helium extremely fast due to its large mass at the point. These are the results that I got for the different runs of the simulations. The graph on the top is the simulation that I used the 128 network for, while the graph on the bottom is the simulation that I used the 21 isotope network for. These graphs show the composition of each isotope at each portion of mass throughout the star at the endpoint of each of the simulations. The lines are mostly straight because the stars are well mixed, so the elements are typically well distributed throughout the star. Some lines in the 128 isotope simulation are curved because the star has not had a chance to mix the isotopes thoroughly throughout the star. As you can see, there's a fairly large difference in the compositions in the stars. While both show that the star can consist of mostly oxygen, the 128 isotope model paints a clearer and more accurate picture of the star's current state. The reason why the difference in composition is important is because as the simulation runs for longer periods of time, the star begins to burn heavier elements, and this difference will become larger. Thank you so much for listening to my presentation.